Hello, and welcome to the video presentation for EGB320, Mechatronics Design 2, Group 4, covering our soccer playing robot. As part of this unit, we were tasked with creating a soccer playing robot that can navigate around a field, locate a soccer ball, and shoot a goal, while conforming to the RoboCup F180 League rules. The robot was split into 4 separate subsystems between group members: the motor driver system, the Kicker-Dribbler System, the vision system, and the AI and navigation system.
I am Mortasa Hussaini. My subsystem was the drive system. My goal was to translate the robot about the X and Z axis and rotate it about the Y axis with consistency. Create a lightweight system. Use high quality material that is unlikely to fail. I designed an omnidirectional drive system. This provided an additional degree of freedom as opposed to the differential drive and Ackermann steer. This allowed the robot to translate and rotate simultaneously for efficient movement. The motors used were the Polu micrometal gear motors with a torque ratio of 210:1. This allowed for sufficient torque while maintaining a high speed. This product was durable and reliable due to its material. The motor drivers used were the Polu DRV8833. They allowed for sufficient operating voltage and current. A breakout board was manufactured to allow for ease of access to the pins and a neater design. The drive system could take the velocity and heading commands from the AI system and direct the robot to move according to the commands. The robot could move forward with a high speed of 0.16 meters per second and a low speed of 0.024 meters per second.
The Kicker-Dribbler subassembly had a few rules and guidelines that needed to be adhered to throughout the project. The purpose of the dribbler was to control the ball and hold it in place for the kicker to accurately strike it with high repeatability. However, the ball was not to be held with more than 20% of its diameter covered by the robot. The solution of this was to create a bar with high friction that would direct the ball to the center of the robot. A bar was 3D printed and the outside was covered in a layer of rubber bands, as it was readily available cheap material. Unfortunately, the dribbling of the ball was never quite achieved, as the height originally just bumped it away, and then after adjustment, when the robot tried to move, it sucked the ball under itself, preventing the wheels from moving it. The kicker section also had a lot of trouble, as the original 2 designs got ruined by the high-power motor when the motor keyholes were dug out. This was fixed by replacing the motor and completely redesigning the kicker system with material, structure, and function. However, due to the lateness in the project, this wasn't completed in time. Time and space were major constraints for the whole system, but the final design was simplified as much as possible, and thus left plenty of free space. However, the time constraints meant that the Kicker-Dribbler system was never quite completed.
The vision subsystem is an important component of the soccer playing robot, as it allows the robot to see the playing field, locate the objects, and aid the navigation and AI system in determining where to move on the field. To achieve this, image segmentation via thresholding was used. The HSV color space was selected to segment the image over the RGB color space, as it can better distinguish between separate colors. Images captured on the field were imported into an interactive image thresholding program to test for the threshold values of each individual object. Using these threshold values, masks could be created for each object. From this, the center point, bearing, and distance of each object could be found using the threshold masks. The distance and bearing were then sent to the AI system for use in the navigation of the robot. For the AI system, a reactive path planning algorithm was implemented. The algorithm will seek the goal as an attractive potential field, while avoiding the obstacles as repulsive potential fields. The state machine of the algorithm is as follows. It will first search for the ball, then seek out the ball, followed by moving to the correct position to shoot, kicking the ball at the goal, and then resetting back to the first step. In all instances, if the ball is lost, the machine will loop back until it locates the ball and continue forward from that point. The AI system was tested in the VREP simulator. The graphs along the right side represent the attractive field, repulsive field, and residual field. The attractive field tracks the goal, while the repulsive field tracks the obstacles. And the residual field is found by adding the attractive and repulsive fields together.